When we look into the Bohr model of the hydrogen atom and see that it doesn't really work well in certain circumstances and has limitations, other chemists started to study this wave behavior of matter. And in 1994, a scientist by the name of Louis de Broglie put a hypothesis together. And he knew that for a photon, the energy is equal to h nu, or can be equal to hc divided by lambda. From Einstein's famous equation, we also know that E equals mc squared. So if we set these quantities equal to each other, we have hc over lambda is equal to mc squared. If we rearrange this around, we find that lambda, or the wavelength, is equal to h divided by mc. If we say that the velocity of a particle can roughly be approximated as the speed of light, this gives us a relationship that says lambda is equal to h divided by mv. And for this, and in de Broglie's hypothesis, we can apply this to all matter. And we can look at the mass and the velocity to give a characteristic matter wave. So this is the relationship that de Broglie looked at. And this is all dependent upon the wave-like nature of matter. Another big breakthrough happened in 1926. And it's known as the Heisenberg uncertainty principle. And this stems from the dual nature of the electron. And what Heisenberg said is that it is impossible to specify at any given moment both the position and momentum of an electron. And for his work, Heisenberg actually won the Nobel Prize. And at the age of 32, he was one of the youngest scientists to be awarded this prize. So the work of de Broglie and Heisenberg really set the stage for new ideas to come about for the atomic structure of an atom, and it opened the door for a branch of chemistry that we refer to as quantum mechanics. And that's what we're going to look at in the next section.